All right, let's dive into one of the most mind-bending ideas in all of physics, the holographic principle. It's this radical thought that our entire three-dimensional reality, everything we see and touch, might just be an illusion, a projection coming from some distant, flat, two-dimensional surface. So, how could that possibly be true? Let's get into it.
I mean, really think about this for a second. What if everything you think is real, your desk, your hands, the stars in the sky, is just a complex hologram? It sounds like something straight out of science fiction, right? But believe it or not, it's a very real possibility that some of the smartest people on the planet are taking seriously.
Okay, so to even begin to wrap our heads around how the universe could be a hologram, we gotta start with a regular one. You know, like the little shimmering sticker on your credit card. Turns out that little image holds a really deep secret about how information works, and it's the key to this whole wild idea.
So, think about what makes a hologram so different from a regular picture. If you tear a photograph in half, well, you've got half a picture. The other half of the information is just gone. But with a hologram, something incredible happens. If you break it into a bunch of tiny pieces, every single piece still contains the entire image. It might be fuzzier, a little less detailed, but the whole picture is still there, encoded in every part.
And that right there is the big takeaway. A flat, two-dimensional surface can hold all the information needed to project a full, three-dimensional image. Now, let's take that idea and just blow it up to the scale of the entire cosmos.
I know what you're thinking. It's a huge leap, right? From a security sticker to the whole universe? So where's the connection? Well, the first clue, bizarrely enough, came from the most extreme and mysterious things we know of: black holes.
Right, so black holes. They're these cosmic monsters where the laws of physics as we know them just break. And it was by studying them that physicists like Stephen Hawking and Jacob Bekenstein stumbled onto a really deep puzzle, one that pointed them straight toward this holographic idea.
Now to get the puzzle, we need a quick definition for this word, entropy. It sounds complicated, but you can basically think of entropy as just the total amount of information in a system. The more complex something is, the more information you need to describe it, which means it has more entropy. Simple as that.
Okay, so here's where it gets weird. Common sense says a black hole's information, its entropy, should be based on its 3D volume, right? I mean, the bigger the space inside, the more stuff you can pack in there. But the math showed something completely bonkers. The information in a black hole isn't proportional to its volume at all. It's proportional to its 2D surface area. That's the event horizon, the point of no return. It's like everything that ever fell into the black hole got its information smeared across the surface, not stored inside.
This result was a total shock. It went against all intuition, and it forced physicists to ask this incredibly bold question. If nature uses a 2D surface to store information for its absolute densest objects, well then what if it does that for everything? What if our huge 3D universe is actually just the inside of some cosmic system, and all the information that makes us, is really encoded on some vast, distant 2D boundary?
And that stunning idea, that leap of logic, is what we call the holographic principle. It's a really central idea in some of the most advanced areas of physics, like string theory, and it completely flips our understanding of space and reality on its head.
Okay, so the formal definition sounds a bit dense, but let's break it down. What it really means is that the physics of a universe with gravity, like ours, can be perfectly translated into the language of a simpler universe without gravity, living in one less dimension on its boundary. It's this wild idea that you can have two completely different-looking physical worlds that are actually mathematically the exact same thing.
Now, for a long time, this was just a fascinating what-if kind of idea. But that all changed when a physicist named Juan Maldacena found a concrete example. He discovered a sort of mathematical Rosetta Stone that lets us translate between these two different versions of reality.
This amazing translation tool is called the ADS/CFT correspondence. Think of it as a perfect dictionary. It creates a precise link between two kinds of universes. One is a weirdly warped 3D space that has gravity. The other is a simple, flat 2D space without gravity, which acts as the boundary of the first one. And the correspondence proves they are just two different ways of describing the exact same physics. You know, this famous drawing by M.C. Escher is a fantastic way to visualize this warped space. See how the angels and demons seem to shrink as they get closer to the edge? Well, in this weird geometry, they're all actually the same size. The correspondence shows that all the complicated physics of gravity happening inside this disk is identical to a much simpler theory of particles that just live on that outer circle, the boundary. Two realities, one truth.
So, why does any of this matter? I mean, it's a cool mind-bending idea, but what's the point? Well, this dictionary has become one of the most powerful tools in theoretical physics. It's actually letting us solve problems we thought were totally impossible before. Here's how they do it. It's kind of like a brilliant cheat code. Physicists start with a super difficult problem in our world, say, trying to understand the strong nuclear force. Then, they use the dictionary to translate that problem into the other holographic universe, where it becomes a much simpler problem about gravity. They solve the easy problem there, and then, this is the magic part, they translate the solution back into our world. It's an incredible shortcut.
And one of the most important things it's helped us figure out is this stuff called quark-gluon plasma. This is this insane ultra-hot soup of particles that filled the entire universe for just the first few microseconds after the Big Bang. Studying it is literally like looking back at creation itself. To make this stuff in a lab, we have to reach temperatures of several trillion degrees. I mean, it's a number that's almost impossible to imagine. At those temperatures, the forces are so strong that our usual ways of doing calculations just completely fall apart. And that's where this holographic tool becomes absolutely essential.
So here's the bottom line. The holographic principle isn't just some fun philosophical question about whether reality is an illusion. It's a real, practical tool that gives us a whole new way to look at the universe. It's a new mathematical language for understanding the birth of the cosmos and the most fundamental forces in nature.
And that leaves us with this one last incredible thought. The holographic principle suggests we might have been looking for answers in the wrong place all this time. Maybe the deepest secrets of our universe aren't hidden in the 3D space all around us, but are actually written on some distant 2D boundary at the very edge of reality. Makes you wonder, what else is written out there?